So graphs. We discussed last week what the idea of a graph is, nodes that are linked in a certain way. And I showed you an application of a map. I told you that we have several implementation possibilities. Implementation is a list of successors, and this implementation does not does not carry data on the nodes. For this one, we're just interested in the sequence and the connections between links. And then this second one is implementation is a list of vertices, and then a list of edges, and then an implementation as an adjacency matrix. So there are four. There are more, but there are four possible implementations that we are discussing in this module. But there are more ways to handle graphs, and you can read for that if you want to as an enrichment yourself. So I started with a list of vertices last week. Actually, yes, I started and I got to there, adding nodes, and I also did remove a node. So this morning I just want to have a look quickly at add successors, remove a successor, and then those few sections before we carry on to implementation as a list of edges. So if we open the Visual Studio example, it's important that we understand how the graph is implemented with the embedded node. That is important. An embedded node inside the graph class. The graph class is, of course, generic. And then there's an embedded node in it, and you should know what the fields are that are in the embedded node. The value one, the one that we actually need to save the data in, that is of type T. And then we have a list, note a list of successors, which is also of type node. So that's a recursive definition. Inside node, we have a list of nodes. So it's things of the same type that follows or are connected, if you want to the current one that we're working with. And then a parallel array, an array where the indexes correspond with weights. Now, of course, that weight can be a double. It does not have to be an int. Depends on your scenario. It can also be a double array, for example. Let's say we have a map between towns, and we have two values that are go with the edges. The one will be the distance between towns in kilometer, and the other one will be the minutes of travel. It's not always directly proportional, because depending on the road, if you have a good road, the minutes and the kilometers can be connected in one way, but if you have a bad road, it can be different. So then we will have two values that connect edges. And then we could have a second array that's also parallel. But remember that we are working with a generic class, so the class should not know what the application is. So to make provision for possibilities of multiple weights between edges, we can have an array. So it can be list of weights, for example. So note the implementation of the embedded node and how it works. Then inside my graph class, I carry then an array. It can also be a list, but I can have an array or a list of nodes. So the class user will just declare a graph of whatever type. So the class user decides what the scenario is and for what he needs the graph. And in this case, it will be a string carrying the names of the towns. But that's a single object. And inside this object, the class itself carries an array or a list of nodes. And then we discussed ways to add and remove. And we made use of a helper method, getNode. And just to refresh your mind, we have this convention of U and V, referring to the vertices at the edge points, at the end points of an edge. U and V as the vertices at the end points of an edge. That's a convention. You will find this convention worldwide, all over the internet. If you Google a bit on graphs, you will find U and V as the endpoints. And then we use the capital and lowercase notations for different purposes. We say, all right, U and V lowercase will refer to the values. In other words, the thing that we save on the vertex. And then U and V capitals will be the entire embedded node class, containing everything, also the weights and whatever you want in there. And then we can use the getNode method to convert from the one to the other. That is what I have here below. You can follow that. So if I want to add a node, I first want to make sure that my node does not exist. If it exists already, then I cannot add it, because my nodes in the array or in the graph should be unique. If it's not there, I can carry on to resize my array, and this array that I resize, because this one is initially instantiated with 0 size. I can resize it, and then I can just assign my new node to a specific index. And here we see another use of U and V, this time with an underscore. And in this case, we refer to the indexes of the specific nodes in the array of nodes. So note the U underscore. Remove node, get the node again from the value, check that it's not null. If it's null, we cannot remove it, because then it doesn't exist. First of all, we have to remove all the successors, or we have to remove all the successors from other nodes that have this new node that we want to remove as a successor. And then we can remove it by moving the nodes up in the array. So those were things that I discussed last week. So if we carry on, I can now add a successor. That is an edge between two nodes from U to V. And a successor is just an addition to the list of successors of U. So remember, my node has a list of successors. And when I want to add a successor, I add to that list with a normal list add method. And I have to add something. So the thing that I want to add is V. So look at line 97. Is it line 97? Yes. So I get node U from lowercase u, get node V from lowercase v. They must both be not null, because if they are null, then that node does not exist. I cannot add a successor or an edge between two nodes if they do not exist. And if they are not null, then I can add a successor to U, and that successor will be V. So note that what we do there. And of course, since we are working in parallel, I also add a weight from U. And the index of this one will be the same as that one, so this weight will correspond with V. If I want to remove it, I want to get the nodes, check that they are both not null, get the index of the successor in my list of successors, and then just remove the V as well. I can use remove at here as well, since I have the index, but I need this index to remove the corresponding weight. If I want to get all the successors of a specific node, and then okay, first of all, is there a successor? Just this thing returns a bool. Is there a successor from U to V? Well, then I just use the contains method of my successors list to return a bool. To get all the successors from U, in other words, starting from a specific town, list all successors that go out from there. If we look at the example, if we look at our example, but I want to somewhere up there. No, not this one. I want the graph, the picture. Where's that picture of the towns? Yeah, there we are. Let's say I want to list all the successors of De Wetsdorp. Those will be Bloemfontein, Reddersburg, and Wepener. So if I want to list all those successors, then I need this method. Get all the successors of De Wetsdorp. In this example case, T is a string, so De Wetsdorp string. Get the node that corresponds with that string, and that U will then contain the weights and everything of that specific node. If it's not null, in other words, if De Wetsdorp exists in my graph, then I can just start up with a new list of successors, step through all the successors, add the value of V, and then return that list. So now I have a list of all successors. If I want to have it with weights, I can have a key value pair, and this is something that you need to get used to, please. A key value pair. It's a pair of data. It's a single thing, but it's a pair with two inherent elements, a key and a value, which basic two elements. And the two elements, in this case, the first one is of type T, the second one is of type int. So T will be my key, that will be the Wetsdorp, or whatever string will be. Int will be then the weight, in this case kilometer, whatever the class user decide to use it for. So then I add the value pair. The first one will be my value of the successor I in this index. The second one will be the weight. And those indexes, as we said, correspond. This weight will go with the successor. So that's a way to get all my successors with weights. Now, important, we need to be able to traverse a graph. And we said before that traversal means visiting every node. And then when visiting every node, I must make sure that I do not visit a node more than once. And I must also make sure that I do not visit a node not at all. So we must visit every node once only. So there are several possibilities of traversing. Again, breadth first and depth first. In order, post order, etc. Those possibilities, as we had for trees, they are still applicable here. If we look at our example, it's important now to notice that we do not have a root. So there's no obvious starting point. So when we traverse a graph, we have to specify the starting point. And then from there follow whatever strategy we decide on. So let's say we start at Bloemfontein and we follow a depth first strategy. So if on the same level, things are on the same level, then we can have a convention of let's do it alphabetically. So if we start at Bloemfontein, there are three successors. So alphabetically is De Wetsdorp, the first one. From De Wetsdorp, alphabetically, Reddersburg will be the next one. From Reddersburg, Bloemfontein has already been visited, so the next one will be Smithfield. Then there's only one possibility, Wepener. Then alphabetically we will go to Hobhouse, Lady Brand, alphabetically Maseru, Mafeking, Mohale's-Hoek. That's depth first. So starting from Bloemfontein as deep as possible, go as far as you can until you reach a dead end. Then once we are there, we back up all the way back to the previous node that we did not visit everyone. So if we now, let's say we ended up at Mohale's-Hoek, then we go back Mafeking. We've already visited Maseru, so then we go Wepener. And from there, we already visited the other two, so Zastron. So now I'm a bit confused. You have to write it down. Then back up to Wepener. We did already visit all the others, so we have to go back Smithfield, Reddersburg, We'll have to, I think we visited everything but the Bonshu and Tweespruit at this stage. So you will back up all the way back to Bloemfontein, then to Bonshu and Tweespruit. That will then be a depth first traversal. It's easy if you write it down. Let everybody sign the roll call list. In this block, everybody. So please move it over to the next block. Thank you. So, and the breadth first will do things on the same level. So starting at Bloemfontein, we will do the Wetstorp, Reddersburg to Bonshu. That's on level 1. Then we will go all the level 2s from Bloemfontein alphabetically. That will be Smithfield, Tweespruit. Then all the level 3s from Bloemfontein, which will be Lady Brandt Weppener, I think, if I don't make a mistake. Then all the level 4s from Bloemfontein alphabetically, Masiru, Mafeteng. And then all the level 5s will be Mohalezoek, Zastron. You got it? Right? So we can do two traversals of a graph, depth first and breadth first. Now to do that in code, depth first is simple. It is just recursive as we are used to. So again, there are two methods. My public method is called list all nodes DFT in line 164. My private one is called traverse DFT in line 1679. Again, two methods. Unlike in trees, when we had trees, when we traversed trees, we did not need to check whether we already had a node in the list because there were no cycles possible. But in a graph, it's possible to reach to a specific node in more than one way. So for that reason, we have to add line 181. That is important. And that is the only difference from the depth first that we have from trees, is the check in line 181. So we have to do that extra. If the graph is not connected, meaning we have islands of nodes, then we will also have to add lines 171 to 173. Or not add, to change. 169 will then become 171 to 173 if the graph is not connected. But if all nodes are connected, you can get from any one to any other one, then you don't need 171 to 173, you only can go with 169. So it's a recursive method to traverse depth first through all nodes in the graph. Let me just check if my friends on Blackboard is still with me. Etienne, Mr. Ndecheni, are you there? And there are more than one. I see there are 5 now. Andre, Keith, are you there? Yes, sir. Yes, sir. Thank you. I'm glad. You can. Thank you. You can, of course. What's the word? I have not a nice word in my head. You can cheat me by connecting on Blackboard and then go back to bed. That you can do. I wouldn't know, so that's why I check. I check that they are awake. Okay. But I do think that they are sitting in bed with a black laptop on their laps. Maybe on the cushion, just next to them. So the next way of traversing is a breadth first. Now, breadth first is, as always, no, not always. We can do it differently, and I showed you. And I think there was in the previous project we did a alternative way. But in this case, again, we use a queue for the breadth first. And I did explain this way in which we do this. Use a queue. And again, there's one or two changes from what we are used to in a tree. And this is the thing that we have to add. Line 201. We have to add line 201 from the breadth first strategy that we did in queues. So I'm not going deeper in this one. All right. So now that we can traverse, the next thing that we need to know is a path. A path has two nodes in the method signature. We want to know how to get from U to V. How to get from U to V, and what would the cost be? How far would it be in kilometer if our application was a map? What would the cost be? So simple, it would be to, since we have all the paths, we can just traverse, do as we were doing before, use a depth first or a breadth first, get all the paths, and then we can say, all right, now I can iterate through all my paths and get the shortest one. That would be a very simple solution. That would be in a small graph where I have a limited number of nodes, but in a large graph, as I mentioned last week, that is actually impossible. So there are very specific algorithms that can be done to do that, and those algorithms are beyond the scope of this module, but they are worthwhile studying. Please, you should Google the word Dijkstra. You spell as Dutch, Dijkstra. So Google that. I repeat, Dijkstra, and read. That's very interesting reading. So in order to get the path, we need a stack and push all the, it's as we were doing before. It's recursive. So we use a stack, and as we visit all the nodes, we push them on the stack. And when we get to a dead end, and it's not the one that we want, we pop them, and we pop them as we go back up the hierarchy of nodes that we visited. And then we visit another path, depth first, traversal, or breadth first. And we push again as we go deeper. And if it's not the one you want, you go back and you pop them. And then you follow another path and you push, push, push. At some stage you reach the node where you want to be. Then that would be the stack, the path from the beginning to where you want to be. Now that is in the reverse order because we push as we go along. So we will have to reverse that stack if we then return that stack to the class user. So you will see here, there, that we reverse the stack once we are done with the recursive process. Of course, the class user wants from U to V, and we push the things so that V will be the last one on the stack. So we want to reverse that when we return the stack to the class user. And then the class user will, at this stage, have a path. I want to have a path from Bloemfontein to Lady Brand. I can run this. And there, a path from Bloemfontein to Lady Brand. A path, not the path, it's not the only path, will be Bloemfontein. And note here, this is not the shortest one. Those of you who know the Free State towns. Bloemfontein, Reddersburg, De Wetstorp, Wepener, Hobbehouse, Lady Brand. That is a path. It's not the shortest one. So if I want to have all paths, I put all these paths in a list, and then I go find the shortest one, which is not an efficient solution. I think I am done with the discussion of a list of vertices. I'm sure that you might not be with me all the way, but I need to move on to the implementation. So I hope that the discussion in the tutorial is good enough. I hope that the examples are good enough. And I hope that the video sound quality is good enough so that you can listen to this again slowly in your own time and make sure that you understand. But we have to move on to the other implementation possibility of a graph, and that is the list of edges. Now I want to put this implementation to one side, and I specifically want you to keep an eye on that class node. And then I want to open the other one and put it to the other side. So that we can compare the two. It's actually, the name speaks for itself. The name should speak for itself. The one is a list of edges. The other one is a list of vertices. So compare the embedded classes, the node class in the two implementations, and compare them, put them next to each other, and make sure that we understand how they differ. And once you have this embedded class, the rest of the methods follow by itself. You just follow the logic to do the methods for add and remove, etc. But we have to understand this difference between a list of vertices on the left and a list of edges on the right. On the left, the class node has the value and then a list of successors. On the right, we do not have a list. We have members for U and V, and we have a member for the weight W. So this is of type T. The edges, the constructor will specify U and V and W, whereas in this case, the constructor will only specify the value, and it will instantiate the successor and the weight lists. And later we need methods to add a successor and to add weights. On the right-hand side, for a list of edges, we do not need methods to add successors because there's no such method. We keep track of edges. We do not keep track of vertices. And inside the edge, we have the vertices. Right? It's just the other way around. On the left-hand side, we have vertices, and inside every vertex, we have a list of successors, which will be then signifying the edges. On the right-hand side, we have a list of edges, and edges contain a starting point and an end point with a weight in between. So note the difference between the two, please. Then, once we have that, I can make this a bit larger. The graph class contains now a list of edges. Previously, the graph class contained an array of nodes. Now remember that this can either be an array or a list. It does not matter what you do there, whatever is easiest for you. Mostly lists are easier to deal with. You don't have to resize the thing as you add. But you can use an array as well, as in line 30 on the left. But you can also have a list on the left. On the right-hand side, I have a list of edges, but you can also have an array. It's also possible if you want to. So, fact is, we have a series of edges on the right-hand side. And we have to now add and remove edges as we go along. If you want to implement this graph. The constructor, instantiate my list of edges. It is possible to also keep a list of vertices as a private list. That is optional. It makes working with the graph a bit easier later on, some cases, but it's not necessary. You can get away without it. So you will find that I have commented out some lines, as in line 26, with dash, with / dash dash. And when you see that / dash dash, you will recognize that as a line that you could put back into the class as an optional, which makes life easier later on. But for the beginning, it might complicate things. So let's just get away without it first, and then we can, if we want to, put it back later. So in the constructor, we have to instantiate the list of edges. And when you add an edge, it's a matter of adding to the list, because the list of edges is the list. Use the normal list add method, which will then add an edge, and you will have to then instantiate a new edge. And edges are instantiated with U and V and W, which we get from the signature from the add edge. Now, remember that in a graph, From Bloemfontein to Tabanshu, there's a road, but it is also possible to travel in the reverse direction. And in a graph, you will have to add those different directions. You will have to add those separately. It will be two different edges. Bloemfontein to Tabanshu, Bloemfontein, that is two different edges. If you wanted to make it easier for your class user and not duplicate work, you can have a parameter in your add method, line 45 at the end, which says, yes, there's a reverse possible as well. So then the class user just specify when he creates the class, view, solution, explorer, program. When the class user creates the class or the graph, he can specify true at the end, meaning then the class itself will add the edge automatically. Or if you have a false, is there an example here? No, there's no example here of a false, meaning, let's say roadworks, no possibility to travel in the other direction. There's no example here. If there's a false, then we only add an edge in one direction. So if that is true, we add the edge again, but make sure now we reverse V and U. The weight is the same, and note that we now have false there. If you have, because this is recursive, this thing calls itself. If you now add a true in there, you will end up in a never-ending loop. So you must make sure that it is now false when you call it, so that you don't call it again and again and again. All right, so that is the add edge method. The remove edge method, again, I have to specify. Do I want to remove from what endpoint to what endpoint, and do I want to remove also the reverse edge? And then it's just making use of my normal list methods. And I remove all the edges where U equals, where the U in the edge equals U in my parameter, and where the V in my edge equals V in the parameter. There's my breadth first traversal. Again, I have a queue. Yeah, just a quick note. I saw some people in the previous assignment. I said, I gave you a hint. I said, okay, you must now do a breadth first, but instead of, no, sorry, you must use a depth first, but you should not use a recursive method. That was the question. Use a depth first, but don't go recursive. And then I gave a hint. You can follow the same strategy as for breadth first, but instead of queue, you use a stack. Then people defined a stack, but they still prefixed it with the letter Q as an example. Now that's confusing. Why would you have a stack with prefix Q? So don't do that. The prefix means something. In this case, I just have uppercase Q in line 75. That's my Q. Because it's temporary, it's local, it sits in this method only. I just use Q. But if you name your variables, please name them sensibly so that it does not confuse us, confuse you, and it confuses me. All right, so this is the same breadth first as always, nothing different. And remember that we need that. We need that part there to make sure that we don't add an edge more than once. That is important. You could have that in a separate if statement, but you can also have it in your link where as a Boolean add, and. But that's important. All right, so that would be different from the implementation in trees. That's the breadth first traversal. And here we have separate paths. To find all paths starting at U. So this is all paths from U. Put it in a list of paths. Put it the weights in a parallel list of weights. start the recursion. Note that this one is public. Again, always two methods. One is public, one is private. That's my private one. It calls itself, and it calls itself every time for every successor of a node. So when we worked with trees, we said, all right, recursively, visit a node, and then visit all its children, and then visit every child's all its children. Now we don't have a tree with children, we have successors, which you can imagine, visualize as the same thing. So we step through all successors, but it's important that we don't repeat things, that we don't visit successors that have already been visited, and for that reason we need this part there. And then we just do this recursively. But otherwise, different from the depth first traversal, we have now a stack. In the normal DFT, we do not use a stack, but now we do have a stack. And we push as we go along, and if we reach a dead end, we pop them as well. And once we're done with this whole procedure of get paths, this list will then be all the paths from you, and this list weight will then be all the weights with the same indexes for the paths that we have there. If I want to have the shortest path, again, go read Dijkstra. But in this case, go through all the paths, just find brute force, find the one that's the shortest. That is the easiest way to do this, but Dijkstra is always a nice challenge. And I will do Dijkstra in the next implementation, in the adjacency matrix implementation, which I hope to discuss on Wednesday.